reappearing and reappearing and reappearing. Across these calculations, again and again, we will have to say L by A, L by A, L by A, right? Even in laboratories, L by A becomes a very important factor, right? So what do? We define L by A as another variant, right? What's a variant? You said variant, but sir, here it is written constant. Okay, so think about it. If you have a cell, right? If you have a cell like this, right? Or if you have a solution like this, and let's say this is basically what it is, right? This is the area, this is the length, the L by A. The L divided by A becomes what? Cell constant. Now say you have NaOH here, okay, as the electrolyte. Case A. Case B, say you have KOH here, okay. Case C, let's say you have a weak electrolyte, CH3COOH. Case D, let's say you have, a sparingly soluble salt, and its ions slightly soluble, let's say AgCl. So what is changing? The electrolyte. What is not changing? The cell. So as long as you have a solution of this much volume with this much plates dipped into it, right? If you change the electrolyte, the L by A would not change. And that's why we call it a cell constant. We represent this thing over here by G star, right? Okay. Although G star is not that much of a standard, but you should know that, right? Okay. This is essentially what we have. This, as I've been telling you again and again, just like we have a metallic wire over here in the case of electrolytic cells, we have, in the case of electrolytic conductance, we have this solution and its entire volume, right, as our cell constant. The L by A of this thing will be our cell constant, or G star, right, people? Okay. So for an electrolytic conductor, G star depends on the distance between the electrodes, the L, and the cross section A, right? And this is then again what we have over here, people, right? Okay. As I was just telling you, this remains constant for a particular cell, right? Indeed. That's why it is called the cell constant, right? So basically, G star essentially is equals to this. Also, what we can do is we can, try, and what I'm trying to do is I'm trying to, relate G star with the conductance or conductivity, right? So what I'm doing is I'm placing R in the numerator, R in the denominator. I have L by A over here. Why did I do that? Let's see about that. So I did that because, if I have this thing over here, what do I have? What do I have? L by A divided by R. Okay, let's revisit. This was equals to something like this, right? Okay, I can also call it something like this, right? Okay, all right. Now, if I take this to this side, if I take this over here, what do I have? I have K, or kappa, is equals to L divided by RA. Get it? Right? So I'm trying to replace this entity over here with K, right? And that is what I just did. So a cell constant essentially turns out to be its resistance multiplied by the conductivity, right? Okay, so what we can do is, if you know the cell constant, well, you can easily measure that, right? In laboratory, it's the cross-section area of the electrodes and the distance separating them. That is very easily measurable, okay? Then resistance also can be measured. You know you're passing a certain current, right? You have an ammeter, okay? You know a certain voltage is there. That also is measurable. So using those two, resistance can also be measured. So if resistance can be measured, voltage can be measured. If resistance can be measured, cell constant can be measured. So can also be measured the value of conductivity, right? Okay.